It's been our pleasure over the last year to host Dr. Mojarro. He's spent the last year on sabbatical from the University of Zacatecas, but he spent it in El Reno, Oklahoma at the USDA Ag Research Service laboratory there, developing a decision support system to sustain the Calera Aquifer. And Dr. Mojarro will tell you a lot more about the Calera Aquifer, but it's a very similar situation to what we have with the Ogallala Aquifer. It's being used at a faster rate than it's recharging. So they're working on developing ways to help sustain that aquifer for a long time. So without further ado.
Okay, thank you. Thank you for the introduction. And thanks to Texas A&M University to be host of my person. Well, this afternoon I'm going to talk about one of the most important issues to the international scale is the water issue. Water and quality and quantity, I think every country is facing this kind of problem. In this case, I'm going to talk about groundwater quantity. We were working for the last 2 years in this project. We built a multidisciplinary team. You know, well, maybe the professor knows more, that to build a multidisciplinary team is very difficult, I think, in any country. But in this case, we got some national and international institutions that are collaborating in this project. Some of the researchers coming from ARS, Texas A&M, in this case the Institute of Water Resource of Texas, and University of Georgia, and this is a National Mexican Institute of INIFAP. This is the use of water is in this on the piece number quotas. This is a Mexican Institute of Water, and this is my university. Today I'm going to talk about a decision support system for the sustainability of the Calera Aquifer in Mexico, Zacatecas, Mexico. Basically, in order to Calera project should be landing, we use the Ogallala project platform. From 2007, we start working together. We plan to make 3 workshops with it in order to get much of the information to use basically the SWOT model. This afternoon, the presentation of line is basically the calibration of the SWOT model. We use ET, crop biomass in recharge, to calibrate the SWOT model. The next activity is about we tested 5 hypothetical scenarios on water recharge, ET, erosion, surface runoff, and finally we did this kind of activity. What is the potential impact of climate change on the region of the Calera Aquifer? Where is located? Well, this is the Mexico country. To the north is Murray State, Belize, Guatemala, in the south part. This is Zacatecas, it's in the middle. And the Calera watershed that I'm going to talk about is in the middle of the Zacatecas state. This is the limitation of the watershed. 2 major things here. We have the 2 largest cities at the state level in this region. One is Zacatecas City, another one is Fresnillo City. In the middle, this is important with I think 1 or 2 slices. We're going to see why Calera is another municipality. It's very important for the region too. Water use, in the case of the Calera, 80% of the total extraction is used by the agriculture, 13% urban, 70% the industry, less than 1% is used by another uses. let me tell you one thing that why we use the Ogallala platform. In the two aquifers, we are going to see so many similarities between them. So one of them is that 89% of the total of the Ogallala aquifer, 89% is extracted, is used, and is used by the agriculture. There is one similarity that both sectors in Mexico and Ogallala, they consume much of the water. Why the Calera Aquifer? Well, 70% of the total population at the state level is living in this region. 73% of the gross internal product and 13% of the total employees are produced in this region. One more thing, the largest factory is at the level of the state is localized in this region. This is the Corona Group that they produce beer. We use so many these kind of workers in the field to collect most of the products. How is the weather in the Calera region? Well, we have as a annual mean of 431 millimeters of precipitation. 75% of them is localized only in four months, and the rest of the 25 in the another 8 months. Here is another similarity with the Ogallala Aquifer. They got 170 millimeters of precipitation as a mean. This mean is coming from 3 weather stations: Calera, Fresnillo, and Santa Rosa.
So you have 3 crops that will be?
Sorry?
You have 3 different crops?
Oh, this is the dry season. The dry season we have irrigated crops in the summer. In the summer is a wet season. We have rainfed crops. Let's try to see that this box represented the Calera Aquifer. We know that there is so many things coming in and coming out, but in a simple way. All the information or the numbers are here, are millions of cubic meters per year. That information is coming from the National Commission of Water for 2009. I told you that on the top of the picture, we see one more time the 3 sectors. The total extraction is 159, but in addition, we found that the water demand for those 3 sectors are increasing by 2 millions of cubic meters per year. If we assume that there is coming out of the aquifer 1.26, now what is coming into the aquifer, mainly by precipitation, we got 57.6, or irrigation practices 15.5, and lateral inflow is 13.8. So if we make a water balance budget, we got minus 73 millions of cubic meters per year. There is another thing that National Commission of Water tell us, that the piezometric levels are lowered into a speed 0.4 to 1.5 meters per year. We have in these graphics how many wells were in 1992, 1,200, and in 2009, 2,100. So 75 increase in 17 years. The population is growing. 2010, we were 435,000, and some prediction of the population for 2030 will be 535,000 people living in the region. So we don't have much water. I told you, 20% of the population of the level stays living in this region. 73% of the gross internal product is produced by the region. So, but we don't have much water to sustain those activities. So we have to do something in order to decrease this speed. I'm going to use this picture in order to illustrate to you how the farmers try to use the water in the field. Oh, we start here somewhere. The water is coming to the aquifer and it's coming out, by the way, by this pump. And the conduction, basically now all the farmers are using this kind of channel, closed channel. Some of them has open channel like this one. Some water is coming out and is arriving to the ranch and to the delivery to the field. The water, we use this kind of channel sometimes, but I told you most of the farmers are using this kind of channels. So some water is coming to the ranch and to the field. Finally, the water arrived to the field. So what that means? Well, how much water I got recharged, and how much water that water is recharged in the aquifer I left in the root system. Basically to be lost by evapotranspiration in order to produce chili, garlic, alfalfa, corn, dry beans. Here we have the irrigation systems that they use, some of them like this, a few of them drip irrigation. We have here between this one and this one system, full open ditch, full irrigated pipe, close to 20,000 hectares. And for a sprinkle and drip irrigation, we have only close to 6,000. But if you see the efficiency, this is the efficiency of the total efficiency of the irrigation system, 45, 50, 55, 70, and 85. If most of the farmers are using this kind of system, so we lose so many water from here and here and finally here. So the big question is here, how much water is left in the root system? Only in the root system. Well, how looks like the watershed, Calera watershed? Those pictures were taken in the first workshop from Dr. Perry Hall from Bushland, Texas. This is the highest level of the watershed. You see, not much soil is left. I don't see any tree. Maybe at the end, maybe nopales or huizaches, but not much. These two pictures are coming from the middle level of the watershed, where you can see some kind of grasses. Maybe those are nopales, cactus. You see this one? We use this kind of land to produce grain-fed corn and grain-fed beans, actually. And this one is the valley, where we have much of the irrigated land and rain-fed land. Here is an example of irrigated land, but most of them here are rain-fed land. All the specific objectives. Well, first we had to calibrate the SWOT using those target variables. Here is a chart. We use this one in order to see how many pieces we have to put together in order to run the SWOT and calibrate it. On the top is all the information that we needed. Also, weather information and some practices of the farmer used to management the crops. And finally, we got the calibration of the SWOT model. Those three pictures, basically this one is new land use map that is required to run the SWOT model. But this one is what basically we use some Landsat thematic mapper, and from the field my student went with GPS and target the crops in the field: chili, garlic, corn, etc., etc. Well, we tested how SWOT simulate the target variables. We used two ways. One was the graphic. We make a graphics and compare the observed value and the simulated value. And we use three statistical tests: notch coefficient, p-bias, determination coefficient. Here is coming the result for the calibration, evapotranspiration, average annual recharge. It was calibrated, SWOT was calibrated at the annual step. This kind of information I haven't seen in the literature. I think it's the first time that I'm seeing the literature. Well, the SWOT calibration is made basically with because the watershed the watershed has gauges in order to measure the water flow or the quality of the water. In this case, we don't have any gauge to measure the water flow. I have to be honest, for this way we use a combination measured and estimated values to be observed values, and the other ones are simulated, the blue ones. For corn rainfed, beans, sorry, this one is rainfed, and this is the natural vegetation. In this case, we put together all the natural vegetation. For those three that I'm talking about, we use 95% of the total precipitation as evapotranspiration. The rest of the information is coming from the field. Basically, that kind of work has been done by the INIFAP, the another institution that is collaborating in this project, and my university. So we define that every differences between the estimated and the observed value has to be between -10 plus 10 here. And for in this case, we got all the values are in this range. Now, if we move to the recharge, the aquifer, in this case, we use two ways in order to estimate the recharge. We use, for this particular aquifer that I told you this aquifer has so many similarities to the Ogallala. Some studies on Ogallala aquifer use 3, 4, or 7% of the total precipitation is recharged to the deep aquifer. In this case, we use 3% of the total precipitation is coming to the recharge to the aquifer. And another one, another component of the recharge is coming from irrigation practices. In this case, we use 8% of the total volume is applied irrigation is coming to the deep aquifer recharge. So, one thing very important, I told you that this kind of information the first time, this is the crop, drip irrigation, alfalfa, furrow, open ditch, alfalfa, gated pipe, alfalfa, sprinkle irrigation. So, is the crop under different irrigation system? The same here. Alfalfa, drip irrigation, alfalfa, furrow, open ditch, alfalfa, furrow gated pipe, alfalfa, sprinkle. So this kind of information the first time that I've seen the literature. The same one. We use this range in order to test if the simulated values are between -10 plus 10. This value. For biomass, very short. We made two calibrations. In the first calibration, we didn't get good result for garlic and chili. And you know why? Because in the SWOT documentation doesn't have the crop characteristics for chili and garlic. We use onion and bell pepper for the first calibration. In 2010, we worked in the field and reviewed some literature, some papers, and we got another information, and we ran one more time, and we get good values for garlic and chili. And you see that differences, the simulated and the observed values are between -10 plus 10. And here in this table is the statistical analysis. This is the target variables, the mean target, the mean simulated, standard deviation target, and simulated. This is the first statistical test, p-bias. The efficiency coefficient, it has to be close to 1. The determination coefficient has to be close to 1 in order to that the values that the SWOT is simulated, they are good ones. And in addition, we use the differences between observed and simulated values -10 plus 10.
Is this annual?
Annual basis.
Annual
Exactly.
basis.
Yeah. So the main conclusion that we feel confident that the ET, deep aquifer recharge, and biomass parameter values obtained for each land use, remember, if you have been look at or use SWOT, is divided in subbasin. Each subbasin has HRU. In this case, we got 626 HRU and 24 subbasin. So, those variables are representatives of the hydraulic process in the Calera watershed. We don't use the classic way to calibrate SWOT model. That's why we said that this approach, we use ET, biomass, in deep aquifer recharge to calibrate the model is another way from the classic way that the people are doing. So that's what we recommend, this kind of the approach in order to calibrate the SWOT model. And in addition, we didn't have so much information. I told you, we estimate some kind of information to take in consideration to run the SWOT model. And I'm very sure not only the Calera watershed doesn't have information or doesn't have a gauge to measure the water flow. There's so many watersheds around the world doesn't have this kind of hydrologic equipment to measure the water flow, the quantity, the quality. Those pictures are coming from the different workshops that we have. The first one, this is Alan Jones. This is the second and the last workshop. These two guys represent the user. The quotas I told you in the first picture, those are the representatives of the users, water user. The second objective for this afternoon is, well, as soon as we calibrate the SWOT model, well, we would like to do the next step is to test some hypothetical scenarios in order to reduce the water depletion rate. Remember, 0.4 to 1.5 meters per year is the water table is lowing. So, the first hypothetical, we want to quantify the change. For open ditch, all the surface are under full open ditch has to change to sprinkle and drip irrigation. And also the crop system. Some surface of dry beans, red chili, and garlic has to change to canola. And see what is going on with aquifer recharge, runoff, and water depletion rate and evapotranspiration. In addition to, we would like to quantify the change of land use of these kind of crops, corn and beans, change to rangeland and pasture, and see what is going on with those hydrological variables. And finally, analyze what is the potential future climate change in the region. This is the information that the user what the user told us what they would like to see in the future. They told us, well, we wouldn't like to see this kind of irrigation system. No more full open ditch. This surface has to be moved to sprinkle and drip irrigation. This is one. And the other one, they said that they would like to reduce dry beans, red chili, and garlic, and change to canola for irrigated crops. And here, well, they said that they would like to reduce the corn and dry beans and move to grasses and this kind of bushes. One important thing, I have to be honest, the SWOT model was not validated to simulate those changes, even though we use it because we calibrated a specific for the Calera watershed. The scenarios, I think it's important to review very fast, even though that I told you before that what the farmers would like to see in the future. The first is water use efficiency. Basically is the full open ditch changed to sprinkle and drip irrigation. Remember the three sectors, water use is increasing by 2 millions of cubic meters per year. In this case, 1.4 millions of cubic meters per year has to be stopped for the year 2020. The cropping change scenario basically is reduce the surface of dry beans, red chili, and garlic, and switch to canola. The third and fourth scenario I call rangeland restoration scenario. The third one, 80% of the rainfed dry beans and 46% of the rainfed corn land must change to native grasses, 40%. To rangeland, 32 and no, 22. The fourth one, 74 of the rainfed dry beans and 60% of the rainfed corn land must change to native grasses, 53%, and 22 to this rangeland, and 23% to oats crops. Finally, we tested what happened with this scenario number 3 and number 4 when the precipitation changed. We got in the year 1969 177 millimeters, and in the year 1976 640 millimeters. So we tested also that scenario. I'm not gonna talk about each one of the scenarios because it's too much information. Basically, that we would like from the beginning, one of the things that we are doing is create some tools in order to see if when those tools is possible to reduce the water depletion rate. So if you see the three first variables and the baseline, no change, 159 millions of cubic meters every year is pumping from the aquifer. Don't change anything change. Well, this is the line. But if the farmer moves to the first scenario, there is a reduction in ET 4%. If moved to the second scenario, there is a reduction of ET by 10%. Surface runoff, well, there is a reduction for 14% in the first scenario and 20% in the second one. Recharge, we don't have too much recharge, but you know, instead to have 69 millimeters, with the first scenario 57 and with the second scenario 40. Here we have extended this column. We have the, I'm sorry, no, it's not a that column. It's water depletion rate. We have three different values of water depletion rate as a baseline in the scenario number 1 and the scenario number 2. This is the baseline, the blue one, scenario 1 and scenario 2. If the user move from the baseline to the first scenario, they change the irrigation system. There is a reduction of the volume by 13%. And if they move to the second scenario, they reduce 20%, the volume is pumped. And we have here, this is water depletion rate, and this is the millions of cubic meter if they move from the baseline to the first scenario into the another one. This is for the 2020 year. So now actually they are, let me tell you one thing that I almost forgot. This analysis is made on the subbasin number 6, only on the subbasin number 6, because SWAT cannot communicate with when one subbasin to the another one. This is for the subbasin number 6. So we use some these assumptions I'm telling you, that we use the information only the subbasin number 6, and we calculate the volume. And in the same for the first scenario, for the baseline is 15.95 millions. For the first scenario is 12.49 millions of cubic meter, and for the second scenario, almost 10.4. So there is a reduction of the volume by 13 to 20%. There is another study for the same watershed and for the same aquifer. In this case, this is another scientist from Reno, Oklahoma, Georgia. He applied the same scenarios that we did, number 1 and number 2, but he also added information urban demand, industry demand. He put together all the information, the water is used by the agriculture, the industry, and the urban sectors. And he got for the year 2045, the volume is gonna be minus 7.72. So there is reduction of the extracted volume, but not enough to stop the water depletion rate. The water depletion rate found by Georgia is gonna be 0.3 meters per year. So even applying that scenarios that Georgia did, the best scenario for Georgia was a reduction of 50% of the total water for the agriculture business. 50% of reduction for the agriculture business. Since they are using close to 120, so they have to use close to 60 millions of cubic meters. In addition, Jurgen called for a reduction of 10% of the industry and another 10% for the industry. So with those reduction, it's not possible to stop the water depletion rate. But at least there is a reduction in the water depletion rate. Actually, the water depletion rate is 0.69. Remember, look at the other on the top, 69 millimeters per year, and here is 30. And here is in this hypothetical scenario that we did is 52 and 46 millimeters per year, lowering the water depletion rate. Remember that we use the scenario number 3 and the scenario number 4. All this information is only for the scenario number 4, when we change some rainfed corn to range land, rainfed beans to range land, rainfed beans to pasture. And the variable in this case, surface runoff, and the variable here is erosion. If you see, in the future, The farmer used to move in the rangeland restoration, move to change on to rangeland. They reduce the surface runoff, reduce a little bit. Remember, the blue one is the baseline, beans to pasture, and also much reduction with beans to pasture. And erosion, this is the baseline, the blue one. If they move to corn, rain-fed corn to rangeland, there is a reduction almost. If you see, no erosion in the future if they move from corn rain-fed and beans rain-fed to range or pasture. No erosion in the watershed. This is a map that is coming a couple of weeks ago. This is the baseline, land use map baseline. The yellow one is the rain-fed agriculture. If we move for the scenario number 4, if we change all the surface for beans and corn rain-fed, you see not much yellow color on the watershed. What happened with climate change? In this case, Georgian used 16 global circulation models and 2 greenhouses gas emission. The middle and the highest, the same that IPCC is using for the prediction of the climate change to the global scale. So he used those models in order to see if there is a trend on temperature and precipitation on the monthly and annual basis. And he found that for monthly and annual basis, there is increase of temperature in the region at the end of this century. 3.7 in the middle concentration of gas, and 4.7 in the highest concentration of gas. And for precipitation is something that is not very clear what is going on with the precipitation for the Calera watershed. But for temperature, it's very sure that it's going to be increased. But what happened with this temperature in the future for the crops? Here is the main conclusions. With the SWOT model, it was possible to evaluate probably change in ET, aquifer recharge, water depletion rate, surface runoff, and erosion throughout the Calera Basin. In this fashion, it was possible to assess the vulnerability of the Calera Aquifer. And this is important. In spite of the efforts made in switching irrigation and cropping system, a substantial groundwater deficit remains. And groundwater table will continue declining after 20 years at the rate of 0.46 meters per year. Referring to the water depletion rate, it's very clear that the solution to arrive at sustainable exploitation of the Calera Aquifer requires more than switching to the better irrigation system and crops with lower water requirements. The benefits of applying scenario 3 and 4 basically is reduction of the surface runoff and elimination of the erosion. Basically is that if they move from corn to beans, rain-fed to pasture and rangeland. How about the climate change? For the middle concentration of gases, the increase in temperature is going to be 3.7 degrees at the end of this century. At the highest level, 4.8 centigrade. The increase in air temperature is expected to lead to a higher ET values, requiring more groundwater to meet the increased water demand of growing plants and delay efforts to reduce irrigation water. So something else has to be done in the aquifer. Yeah, changing the irrigation system. You know, The Calera Aquifer, I think they have more than 30 or 40 years changing the irrigation system. In the water depletion rate is still falling and falling. The same case for the Calera Aquifer. We started in 1992 with a national program, changed the irrigation system from full open ditch to drip and sprinkler. And for the Calera Aquifer, the water depletion rate is lowering. So something else has to be done in order to stop or reduce the water depletion rate. A new policy has to be imposed by the National Commission of Water to close some wells. Has to be done something different than switching the irrigation and switching the crop with the crop water requirements. Well, we acknowledge to the financial support to USDAID and my university with this specific cooperative agreement, and also to the rest of the people that they are part of this international project. If you see, the Mexican guys are not here, but they know why they are not there. Thank you very much for your attention.